You have to consider the physical timescales. Quenching is a massive thermal shock. If you drop the energy URF to 0.3, you are artificially slowing down the mathematical propagation of heat.
But I'm stabilizing the run.
But your mesh is still moving at physical speed. Your fluid is still flowing at physical speed. You end up completely decoupling the thermal physics from the momentum physics. According to the strict best practices for this scenario, you must set the energy URF aggressively high, between 0.95 and 1.0, to ensure the thermal shock keeps pace with the physical immersion.
I am not convinced by that line of reasoning because you are completely ignoring the spatial distortion.
I'm really not.
Setting an energy relaxation factor to 1.0 on a highly skewed, unstructured moving mesh is like taking the brakes off a heavy truck going down a mountain. The geometry is too corrupted. The gradients will explode.
That is a compelling argument regarding the geometry, but you are assuming the default method of calculating those gradients is immutable.
What do you mean?
How are you calculating the thermal gradients across those distorted cells?
I use the standard default for unstructured meshes, least square cell-based gradients. It is computationally efficient.
And there is the second fatal configuration error.
Fatal again? Come on.
I'm serious. When you use cell-based gradients, the software relies on the geometric centroid of the cell to calculate the flux across the faces.
Right. Standard volume math.
Think of it like trying to balance a large tray with one hand exactly in the center. As long as the tray is perfectly symmetrical, it's fine.
Okay.
But when your dynamic mesh stretches a tetrahedral cell into a highly skewed pancake, that centroid shifts wildly. It becomes severely misaligned with the face normal vectors.
So you're off center.
Exactly. You are no longer holding the tray in the center of mass. The mathematics literally skew. The software calculates a false temperature gradient based on a distorted centroid. And because you have a high URF, that false gradient explodes instantly.
Okay, so if cell-based gradients fail on deforming meshes, what is the alternative that miraculously handles a 1.0 URF?
You introduce the mandatory gradient shift. For any complex geometry requiring tetrahedral or unstructured meshes, which is virtually all dynamic quenching models, engineers must switch to Green-Gauss node-based gradients.
Node-based gradients?
Yes, node-based methods calculate the gradients by averaging the values at the nodes, the actual corners of the cells, rather than relying on a single shifting centroid.
I see.
To go back to the analogy, it's like holding that same tray firmly by all four corners. It doesn't matter how asymmetrical the tray gets, you have a stable mathematical grip on the boundaries.
That actually makes intuitive sense.
It is vastly more robust against cell skewness. If you use perfect extended piecewise linear tables, an energy URF of 0.95, and node-based gradients, the mesh can deform dramatically and the energy equation will remain rock solid.
I am not saying it is impossible, but we have to acknowledge the reality of computational overhead here.
It's heavier, sure.
Node-based gradients are incredibly memory-intensive. They require significantly more computational effort per iteration to average the nodal values before calculating the phase fluxes. We use cell-based gradients because they are efficient.
Efficiency is a double-edged sword.
You are asking engineers to take a massive hit to their computing time to force this so-called compatibility.
I absolutely acknowledge the computational cost. Node-based gradients are heavier. But ask yourself this, what is more expensive? A simulation that takes 20% longer to solve? Or a simulation that runs exceptionally fast for 2 days and then completely crashes and burns your data right at the crucial moment of phase transformation?
Well, when you put it like that,
efficiency is entirely irrelevant if the math diverges.
That is a fair point. A slower, memory-heavy run that actually reaches physical time is vastly superior to a fast failure. But this brings up a massive practical issue regarding validation.
How so?
We are talking about massive, multi-day production runs on high-performance computing clusters. Even with extended data tables, a high URF, and node-based gradients, I can't just hit compute, wait 4 days, and pray that my settings hold up during the peak of nucleate boiling.
No, definitely not. Don't do that.
How can an engineer definitively prove their setup is stable and accurate before committing those resources? I need a practical roadmap here.
You need a strict pre-flight check. The validation protocol here is entirely non-negotiable. First, You have to fundamentally change how you monitor your energy residuals.
Change how?
In standard steady-state aerodynamics, maybe you settle for residuals that flatline at 10 to the negative 3.
Sure, that's pretty standard.
You cannot do that here. You must not settle for merely stable flatlining residuals. True physical convergence in a highly transient quenching simulation requires the energy residuals to drop by at least 3 orders of magnitude within every single time step.
Dropping by 3 orders of magnitude per time step in a transient, multi-phase simulation?
Every single step.
Yes. That is an impossibly strict standard. If I am dropping from 10 to the negative 2 down to 10 to the negative 5 in every single microsecond time step, I'm going to need 40 or 50 inner iterations per step. You are turning a 4-day run into a 3-week run.
Quenching is a brutal physical process, and the mathematics required to capture it are equally brutal.
But 3 weeks?
If you do not fully resolve the energy equation down by 3 orders of magnitude in a given time step, that remaining energy error doesn't just disappear.
It carries over.
Yes, it accumulates. And when the mesh moves again, that accumulated error acts as a false energy source, leading straight back to divergence.
So the computational cost is simply the price of admission for this level of physics?
Unfortunately, yes.
Okay. But how do I test that residual convergence without running the full massive geometry?
You never run the full multi-day production model first. You insist on running a simplified pilot test.
A pilot test? Like a submodel?
Take a basic geometry, a simple cylinder or a block. Apply your exact dynamic mesh settings, your exact extended piecewise linear tables, your exact node-based gradients, and plunge it into the fluid for just a few simulated milliseconds.
And what exactly am I looking for during those few milliseconds? Just a residuals check?
Residuals, yes, but more importantly, you are conducting a physical sanity audit.
A physical sanity audit. I like the term.
You check the initial time steps for visual physical anomalies. You look at the temperature contours on the surface of the part. Are you seeing speckles?
Speckles? What do you mean by speckles? Like isolated nodes showing weird temperature spikes?
Exactly. A checkerboard pattern on your temperature contour. Single cells that are suddenly 200 degrees colder or hotter than their immediate adjacent neighbors.
Okay, sudden, sharp discontinuities in the thermal gradient.
Right.
But hold on a second. How do I differentiate a numerical speckle from a physical reality?
What do you mean?
In a quenching process, you have nucleate boiling happening. You have localized vapor bubbles forming, collapsing and pulling massive amounts of heat away from very specific points on the metal surface. Localized temperature spikes are a physical reality of multi-phase cooling.
That is a critical distinction, absolutely. But there is a clear difference between physics and numerical failure.
Which is?
Physical nucleate boiling, even localized, creates a continuous gradient. The heat diffuses through the metal adjacent to the vapor bubble. A numerical speckle has no physical diffusion.
It's just a harsh jump.
It is a harsh mathematical checkerboard. One cell is 800 degrees, and the cell right next to it, sharing a face, is 1,000 degrees with absolutely no gradient in between.
Oh, I see.
If you see numerical speckles, it is a dead giveaway. It indicates either your material table is still too coarse in that specific temperature band, or your mesh distortion has finally exceeded the limits of even the node-based gradients.
So you catch it early.
Exactly. You identify this on a 20-minute pilot run on a simple cylinder, you refine your mesh or your tables, and you fix it before you commit to the 3-week production run.
I have to admit, that forces a profoundly different approach to how we handle the solver. As we wrap up this discussion, I want to summarize my evolved perspective here.
Go for it.
I came into this arguing that piecewise linear models and dynamic mesh motion are fundamentally structurally incompatible. But breaking down the enthalpy physics, the mathematical blindness of truncated data tables, and the geometry of centroid-based gradients, I see that what I previously viewed as a software limitation is actually a profound issue of configuration discipline.
It usually is.
I am absolutely going to implement that simplified pilot run before my full simulations. And more importantly, I am going back to my material databases, extending those tables well beyond the physical maximums to accommodate the solver's numerical guessing is a critical safeguard I just hadn't considered.
It'll save you a lot of headaches.
I still maintain that the computational overhead of node-based gradients and brutal residual drops is a heavy burden, but, well, if it prevents a crash, it is necessary.
And to summarize my stance, I firmly stand by the fact that piecewise linear models and dynamic mesh motion work perfectly together in the CFT environment.
If you treat them right.
Exactly. As we've explored today, they are highly unforgiving of relaxed inputs. The software will not save you from your own data boundaries. The incompatibility myth exists simply because it is vastly easier to blame the code than to admit our data is brittle and our gradient methods are cutting corners.
Fair enough.
Meticulous discipline in defining those material tables combined with robust numerical schemes like node-based gradients and demanding deep residual convergence is the only path to trustworthy results.
Digging into the microscopic details of simulation parameters really reveals that what we often perceive as hard technical limits are actually just the boundaries of our own user precision. The software is capable, we just have to be exacting enough to guide it through the math.
Beautifully put.
I think there is a lot more to explore in this material, especially regarding how these setups handle the actual multi-phase interactions of film versus nucleate boiling, but that will definitely have to be a topic for another day. I'd highly suggest our listeners rigorously audit their own material property tables after this.
For anyone following this simulation debate, the ultimate engineering tip for heat treatment in CFD is this: trust the physics, but relentlessly verify your mathematical inputs.
Well said. We started today by talking about the frustrating reality of instant solver crashes, assuming that digital worlds simply couldn't handle the violence of the real one. We realized that while the physical universe naturally maintains its own continuity, our digital simulations demand absolute perfection from us to keep the illusion alive.
They really do.
A single missing data point or a shifting cell centroid is all it takes to break reality. Thank you for joining us, and we leave you with this question to consider next time you hit compute. Is your simulation crashing because the physics are impossible or because your mathematical map ends right where the real fire begins?